welcome back to RandomMathsInc, and today I'm going to be talking about a physics class called electricity and magnetism. So let's get right into it. So what is electricity and magnetism? Well, as the name suggests, this subject deals with two different things. It deals with electricity and it deals with magnetism. Now, collectively, we can also call this E and M because it's a lot shorter. So sometimes I'll refer to it as E and M. But basically, in this class, we talk about two different things. We talk about electricity and we talk about magnetism. So what are they? You might have heard of it before, right? Electricity, you might have, for example, you have electric forces, which you might have seen before in other physics classes. So if you have things like a positive charge, two positive charges, for example, they'll repel each other. Or if you have a positive charge and a negative charge, they'll attract each other. Those sorts of things. These are the electric forces. In specifically, you might have heard of them as Coulomb forces. Magnetism, you have something very similar. You might have, for example, a bar magnet, right? And they might attract each other. If, like in this case, they'll attract each other. If this one is flipped, they'll repel each other. But you might have also seen, well, magnetism in other cases. Maybe you have a piece of wire like that, right? A piece of wire with a current running inside of it. You can, like, for example, take a compass, and you'll see that the compass points in a certain direction, following the current within the wire. It'll sort of follow this pattern, right? There'll be sort of a loop. And, you know, why is there a loop? Those sorts of things. These comes from, well, magnetism. Now, it turns out that electric forces are from charges attracting or repelling each other. And if you think about this case in particular, well, the current is just moving charge, and the moving charge in the wire is what's causing the currents, and the current itself is what's causing the magnetic forces. So in fact, electricity and magnetism both are sort of related because they both talk about forces between moving charges. So in electricity and magnetism, you have, you know, this quantity called the electric field and the magnetic field, which are both really related to the electric force and the magnetic force, in the sense that the electric field is, you know, a property that sort of tells you about the forces, the electric forces. So for example, if I have like an empty space here, and in this empty space I have one positive charge like that, then, you know, if I have another charge here, just a small charge Q, it will have a force exerted upon it because of this positive charge. If this Q is a plus Q, then it will be a force acting outwards. If it's not, if it's a negative Q, then it will be going in the opposite direction, right? And in fact, if you move Q anywhere, then you can sort of work out like what the force in that place will look like, right? If I instead move Q here, its force will be like that. And you can keep drawing like this vector everywhere. And eventually you get this sort of force field all around this positive charge. And this force field is the electric field. In more particular, in more specific case, is that the force on this positive Q, wherever Q is, will be equal to the size of the charge Q times the electric field. That's how the force of, like, on a charge is defined, is going to be equal to this. And if we have a particular charge, we can define the electric field in this way. You might have seen diagrams like this before, where the positive charge sort of radiates out electric field, and if you have a negative charge, the electric field sort of goes in the opposite direction towards that negative charge, that sort of thing. In magnetism, you have something very similar. You have the idea of the electric field, the magnetic field, but they convey slightly different meanings, in the sense that rather than, you know, being a nice equation like this, it's defined using, well, another moving charge. If you have a current like running like this, and I have a charge Q moving in this direction, then the force will be acting perpendicular to the way that it's direction that it is moving at. And so from this property, the force is like that. So you can define a magnetic field that loops around this wire. You can define a magnetic field at that point in particular to be, you know, in some direction and have some magnitude such that the force acting upon that charge will be equal to QV cross B. So it's sort of a definition thing. You define the magnetic field such that this applies. This is also like sort of the right-hand rule thing. This is called the cross product. But if you've heard of the right-hand rule before, it's basically that, right? So if you have, for example, charge moving that way, and you have a magnetic field moving that way, then the force must be going in that direction. That sort of thing. So, you know, you have the electric force and you have the magnetic force, and they're both really related to the electric field and the magnetic field, which are two quantities that you might have seen before in like earlier physics class. So as I mentioned, like in a current moving wire, you can put compasses around it and you can see the shape like looks like this. But if you have a magnet before and you, for example, place iron filings on it, you can see that it sort of makes this shape, right? It sort of like looks like it's sort of like these lines of all around the magnet, that sort of thing. And this, in fact, is the magnetic field lines of a magnet. So in E&M, you sort of study like all of these things. You study like, why does the electric field look like this? Why does the magnetic field look like that? And why, for example, does something like a magnet have like magnetic charges or create a magnetic field in the first place? And in electricity and magnetism, E&M, you basically work with a set of 4 different equations. And these 4 equations are sort of the pillars or the fundamentals to E&M. These 4 equations collectively are known as the Maxwell's equation. And if you think this name is familiar, because I've talked about it before, I have a series on it which is incomplete. I still want to complete it, by the way, so just take a look forward to that. But basically these are the Maxwell's equations. Now these equations look extremely complicated, but I will show you that they are not, because they actually describe some things about the electric fields and magnetic fields that you might have sort of seen already if you like have heard of the electric fields and magnetic fields before. They just described in a very complicated mathematical way, and I will not get into the notations, but I'll describe things about what these equations basically says. For example, if you think about having a positive charge, that sort of thing, then, well, you know, the electric field sort of radiates outwards like that, right? But if instead I have like an even more positive charge, maybe like 2 plus, like that's a really bad notation for it, but like maybe like there's like 2 positive charges there, then you know that the electric field must be even stronger because there's more charge concentrated there, right? In the opposite sense, if you have a negative charge, then you know that the electric field must be going in the opposite direction, right? And if you have no charge at all, then you know that the electric field there, well, can't really be radiating out anything or anything going into it, because it's not positive, so nothing radiating, and it's not negative, so nothing's going in. So if you have an electric field, it might just pass through it, for example, right? So these ideas is basically what this equation is saying. That's something called Gauss's law. It's basically talking about how the electric field sort of diverges or goes into a certain place, and that just depends on, well, how much charge is concentrated in a certain place. And as you can see, the electric field sort of only diverges out or contracts. You can't really create an electric field that loops around itself, right? Like how can I arrange a charge so that the electric field looks like that? Well, the answer is, well, you can't. And that is the consequence of this equation. This basically says that electric fields can't loop around itself, that sort of thing. You can't have an electric field that sort of goes round in a circle. And, well, this also leads to other consequences as well. That, for example, if you have an electric field, if you have 2 points, point A and a point B, and you want to move around it through electric potential, an electric field, well, the amount of work that you need to do to get from point A to point B will be the same independence of which path you take. That sort of thing, that also comes out from this equation as well. And, well, these two things, these 2 facts about electric fields are 2 geometric facts that you might have sort of seen, or you might have been able to think about or observed, but now they are described in more compact mathematical notation. And you can do something very similar for magnetic fields as well. So, for example, well, as we've mentioned, magnetic fields comes from, you know, current carrying wires, right? So, you know, you have a wire carrying a current, there'll be a magnetic field like that. Well, and again, you can rotate it around any way you want as well. But if now I have an even stronger current running through there, then the magnetic field will be even stronger, right? So more current equals stronger magnetic field, or basically magnetic field that loops around a lot more, right? The loops are stronger. Basically, this equation that basically tells you that magnetic field that is created will be looping around a current, right? And it also tells you the shape of the magnetic field, that it tends to be in a circle sort of thing. Now, think back to magnets example, right? If you think about having a magnet, you might have done this before when you were a kid. Break a magnet into two, right? Then you have a north pole, and you have two pieces of a magnet. But it turns out that the two pieces of a magnet doesn't create a north pole and a south pole. It actually creates two smaller magnets, with both of them having their own magnetic fields, right? And you might thought, like, magnets have got like a north pole and a south pole. Can I create a magnet which is just a north pole, or a magnet which is just a south pole? And the answer is no. You cannot have like a magnet that looks like that, right? If you think about like magnets like this, if a magnet just has a north pole, then the magnetic field lines might just move out like that. And if it just has a south pole, it'll just move inwards like that. But it turns out that physically you cannot have this, and this is a consequence of this equation. This basically says, similar to how electric fields can diverge and converge to a certain point, this basically restricts magnetic fields from being able to do so. You cannot have this case, and that's the consequence of this equation, basically saying you cannot have magnetic monopoles. And so, again, as I've mentioned, these four equations perfectly describes the nature of these magnetic and electric fields. And we go into a lot more maths about like how exactly they do so, that I've not mentioned in this video. And but you can like take a look more into like how they do so as well, and what consequences we can get out of it, because these are just the really basics, but then you can get onto like more complicated ideas in regarding to them as well. And this is not even the entire story. So, like once you have these quantities here as well, then you can start asking even more questions, like, like how electric fields and magnetic fields, in this case, looks like they are sort of independent with each other, but it turns out that they also affect each other in some ways. So, for example, if you have a magnetic field running like that, and you have a wire that loops around like this, right? And this wire is spinning. If you spin this wire around and around, then the electrons inside this wire will actually start to move, and you will get a current within this wire, within this loop here. The current will be moving, which means that if you have a magnetic field, and you have something which is, moving within this magnetic field, it actually creates a current. If you create a current, well, then that means there must be a charge inside there, and that charge is being pushed. There must be a force on the charge, and that is due to something creating some electric force for that charge to start moving. And, this is called Faraday's law, I believe. And there are also other phenomena, things like, if you have a metal tube, and you have a piece of magnet falling down that copper or aluminium tube. Did I say magnetic tube? I meant like a copper or aluminium tube, and you have a piece of magnet falling down it. This magnet will actually slow down, because the magnetic field is actually creating, well, it makes the charges in here move, and that charge creates another magnetic field that counteracts this falling magnet, and then the magnet slows down. Effective Lenz's law, that sort of thing. And it turns out that the electric field and magnetic field then also interacts with each other, which means that this equation is actually wrong. There's like extra correction terms sort of thing within the Maxwell's equations as well, which is irrelevant to our video. It basically also points out like that, like you actually learn about, like, for example, like how these equations affects nature, or basically you can look at things that you might know in nature and properties that you might know, and then you can think about how you can describe that more rigorously. And once you have like a math foundation down for it, you can start to go on and ask other things as well that comes from it. And so basically, yeah, that is, well, this class in electricity and magnetism, where you just study the properties of these two things. And it's a really fascinating class. It's a really mathematically heavy class as well, because as you can see, everything is just described in terms of calculus. But it's, you know, that's what physics is. It's basically using maths to describe things in nature. So, you know, use of calculus like this is pretty expected. But it's a really fun class as well, because of how challenging it is. Especially because I took it like pretty early on, like maybe like my first or second year. This is when like I sort of started to do it. It's one of the first physics classes I took as well. But at least, unlike in high school, you actually unravel a lot of the things that you might have seen in high school, and you sort of ask some of the more fundamental questions about different things like that. And I think that's probably a good introduction to what electricity and magnetism sort of is. And again, if you want to know more deeply into like what these equations mean, I have a series on it. Go check it out. It's incomplete, but once it is, you can also watch the whole thing as well. And yeah, basically, I didn't get into the maths too much, so hope no one minds that. But anyways, thank you very much for watching this video on electricity and magnetism. This is another episode of 12 classes, and I'll see you again tomorrow when I talk about a maths class that actually helps a lot with the physics.